All right. Let's open up with a, it's actually good, a good problem to fold everything all in together. We're gonna do 630, which is right here. And I'm gonna take a, I'm gonna copy it. We're gonna go through this entire mechanism. We're gonna calculate delta H for all the steps and do nucleophile, electrophile, all that stuff. We're gonna do that, everything for this one problem. So let me capture it and put it on another page so we'll have room to work. Uh-oh, no, don't want that. And we're gonna come back and finish that that handout. Get my life right today. All right. Let me just add a page in right here. All right, let's do this problem. And we're going to talk about the, come on, you got to be freaking kidding me. Kristen, you jinxed me. I'm about to kick you out of the meeting. There we go. All right, so let's go through this particular question right here, and we're going to blow it up some more. We're gonna do everything that we've been doing. We're just gonna do it on this one problem. All right, so let's look at the first step, which is going from right here to here. We're gonna put the arrows in for that step too. So I'm gonna redraw it so everybody can see it and follow and all that good stuff. So I got my epoxide plus HBr. All right, so let's do that. Let's put the arrows in for that first step. And we're gonna label everything because this is a good problem. It's got a lot of meat on it. All right. So look at what's here and tell me how I got from here to there. What did I do? What does it look like I did?
Attacks oxygen and hydrogen.
So hydrogen and oxygen, something happened between them, right?
Mm-hmm.
Right. So it looks like what I did was a proton transfer, right? So let's do this and this. If I'm doing proton transfer, is that acid base or nucleophile electrophile?
Acid base.
Acid base chemistry, good. It's similar, right? In that the proton is partially positive and what's attacking it, it has a pair of electrons, so it's partially negative, but it's not nucleophile electrophile chemistry. Which one of these would be the acid? What do you think?
HBr.
Good. This is my acid. That makes this my base, right? So now we're going to get this intermediate. Right here, OH, lone pair plus charge. Right, this is an intermediate. What's the difference in an intermediate and a transition state? Somebody help me.
With the transition state, the bonds are partially broken.
I agree with that. So what does that mean? Does it mean, what does that mean in terms of whether I can isolate it or see it? Is it real or is it just is it theoretical? All right. The difference in the intermediate and transition state is the intermediate is a real species. I can actually trap it and see it. The transition state is only theorized, right? I can't see it. I can't touch it. It's an imaginary structure. Let's do that here. So what am I doing going from, we're going to call this A and B. What am I doing in between A and B again?
Proton transfer.
Okay, proton transfer. So I just made a bond between H and let me put over here Br minus. Okay, let's not forget that because I lost bromine. And then it has 6 electrons around it here. All right, so I made a bond between O and H. Is that right?
Yes.
And I broke a bond between H and Br. Is that right?
Yes.
So this, if I were to draw the energy diagram, let's matter of fact, let's calculate it first, and then we'll know whether it's exothermic or endothermic. We'll know whether it's fast or slow, all of that. So bonds broken in this first step. Bonds broken would be HBr, and then the bonds formed would be, let me not write that because somebody gonna think I'm trying to be funny. OH, right? Let's go up to our chart. So HBr, here we go. So the HBr bond is what? How do I read the chart again? Find H, find Br. Is that right?
Br. Mm-hmm.
And it says right here that it's 364 kilojoules per mole. Is that right? And then yep. I made a OH bond. Is that right? So I find H and then I go over to oxygen, and it says that is 464. Yes.
Mm-hmm.
All right. So let's go back down to here. Somebody remember those numbers. You know I'm old, so sometimes I remember it, sometimes I don't. This is 364.
So it's 364 and 464.
So if I calculate delta H, it's what, negative 100?
Yes.
Kilojoules per mole? Good. So that means that if it's negative 100 kilojoules per mole, is it exothermic or endothermic?
Exothermic.
Highly exothermic, right? Negative 100 kilojoules per mole, that's giving off a lot of energy. And so if it's exothermic, right? What else does that mean? What other terms can we take from this?
Delta G is negative.
Delta G?
Mm-hmm.
Okay, I agree.
The K
Active.
is greater than 1.
Say that again.
KEQ is greater than 1.
Good.
And the activation energy is low.
Good.
So meaning all of that will be a faster reaction.
Yeah, very fast. Exactly. Exactly. So now I can actually write that first step on an energy diagram as exothermic. Is that right? Is that an example of an exothermic curve?
Yes.
Yes.
You see the activation energy right here? That's that distance between reactants and products. That's your activation energy. And it's low compared, and the products are always lower in energy than the reactants. Are we okay with that?
Yes, sir.
Okay. So now, right here, this part right here, that's my intermediate, because this reaction is not done, right? If you look at the reaction, this is the intermediate that you get from the first step. And then there's another reaction that has to happen in the second step. Are you following?
Got it.
Yes.
All right. So Brittany, this is an example of a stepwise mechanism. You have a first step that happens, and now you got another step that's got to happen before you get to the product.
Okay.
All right, so let's do that second step, and let's see if we can get the overall. Dang it, I need to add another page. I need infinite pages. All right, so we're going to start at the intermediate, which is here. That's positive. And we're going to react that with Br minus, okay? And then keep in mind, bromine has 4 lone pairs around it. That's why it's negative. All right, so this is going to hit, it's not going to hit oxygen, right? It's going to hit the carbon. Right, because oxygen can't take anything else. It's got a lone pair and 3 bonds to it. So that's a total of 8 electrons. So it's already got a full octet. So it's not going to hit oxygen. The bromine is actually going to hit the carbon right here. Boom, like that. I think that's how it has it. Or did it hit the top? Or it showed it hitting the top. All right, we're going to match it. It's coming here. Boom. And then I'm going to pop that ring open. Anybody not see that? Right? The reason why the bromine is hitting that carbon is because the oxygen, even though it's positive, it's got a full octet, so it's not going to take another pair of electrons. But that carbon is partially positive because it's connected to an oxygen that's positive, right? So this is partially positive because the oxygen is sucking all the electrons towards itself in that sigma bond. It's a big dipole going towards oxygen, right? So in this step, right here, which one is the nucleophile? Because this is not acid-base chemistry any longer. This is now nucleophile, electrophile chemistry. So which one is the nucleophile?
Bromine.
Bromine, good. That makes this the electrophile. Is that right? And within every electrophile, there's a site that reacts. It's called the electrophilic site or the reactive site, which in this case is here. Right, that's my reactive site. That's where the nucleophile is going to attack. It's not going to attack anywhere else because the whole goal of the nucleophile is to find a polarized atom and attack it, right? And so that carbon is polarized, and so that's where it's going. We're okay with that?
Yes, sir.
All right, so now we have this as the product. Where now this is OH and this is BR. Any questions about that? So let's do the, and again, this is the second step in the overall mechanism. Get into this, I think they had it labeled up top as X, right? So what bonds did I break?
The CO.
Okay, I broke a carbon-oxygen single bond, and then I formed what?
A CBR.
Carbon-bromine single bond. So let's go up to the chart and find those numbers, and then we're gonna plug them in, all right? So I find carbon, and I broke a CO single bond, so that's 360. And I'm working in kilojoules now. The numbers above are in kilocalories. And whatever unit I use, I gotta use it for all the numbers. All right, so CBR is 285. What do you think that step is gonna be, endo or exothermic, just based on what you see? You broke a strong bond and you made a weak bond. What do you think?
Exo.
Let's see. So we broke this was 360 and this was 285. And so delta H would be positive
And
75. Is that right?
yes.
So it's positive, right? Anytime, let me help you understand that. Anytime you break a strong bond and make a weaker bond, it's going to require energy for that to happen. Strong bonds don't like to break, right? So if you break a strong bond and make a weak bond, it's going to be endo. It's always going to be endothermic.
Okay, thank you.
Kilojoules per mole. And the goal, remember the goal is to make strong bonds and break weak bonds. That's the goal. Sometimes that's not possible, but that's always the aspiration, right? All right, so it's delta H is positive. What else do we know? What do we know about the activation energy? It's going to be
high.
opposite. And we know that the Gibbs free energy is also going to be positive, right? And we know that the reaction is endothermic. Is that right?
Yes, sir.
All right, so it's endothermic. And we know what about the KEQ?
It's less than 1.
Less than 1. Means the reactants are favored. Right?
Yeah, it'll be a slow reaction.
Slow. High activation energy. So let's go back up to the chart, the energy diagram. Can we put that second step in? So to go from the intermediate to the product is endothermic. Is that right? It's ugly, but you get it. Well, I hope you get it.
Mm-hmm.
So time is on the x-axis, and then energy is on the y-axis. Right? So this is endothermic. You can see here the activation energy is much higher. That's my intermediate in between. So this is an example of what we call a stepwise mechanism. Right? Multiple steps to get to the product. Right? You see we had the first step was proton transfer, and then the second step was nucleophilic attack of bromine on the epoxide. Let me sneak you some information here too. This compound, you see that cyclic 3-membered ring right here. So a 3-membered ring with oxygen, a 3-membered ether. This is called an epoxide. Might as well give it to you while we're here. Right? It's called an epoxide. And when we get ready to talk about alkenes and how they react, that's one of the main reactions we're going to look at, is how to make epoxides. So might as well sneak you a little information. So this is plus 75. So what's the overall delta H? for the reaction. If one step is plus 75 and one step is minus 100,
Is it negative 25?
it is. So the overall process is what? Exo or endothermic?
Exo.
The overall
Thermic.
process is exothermic. Good. Right? And it's a stepwise process. It's a stepwise mechanism because first you had to activate the ring by doing proton transfer. And then after you activated the ring, you did nucleophilic attack on the intermediate. Is that okay? Are y'all with me today? I know it's Friday.
Yeah,
Yes, we're with you.
All right. I just want to make sure. All right. Any questions about that problem? If you understand this, then we met the goal of this section. If you understand what just happened. If you understand what a nucleophile is, what an electrophile is, what a source and sink is, why somebody tell me, because I'm not going to start a new topic because we're going to start radicals on Monday. Somebody tell me why I took the arrow from bromine to carbon. Why did I start it at bromine? Why didn't I push the arrow the opposite direction?
Because it's supposed to be source to sink, not sinks to source.
Source to sink. That's always the case for chemistry. You never push electrons towards a negative. You always push them away from the negative, right? So this is my source, and this is what? My sink. I promise you, it's a common mistake to just put the arrow going from carbon to bromine, but that's nothing could be further from the truth. If something already is negative, it doesn't want more electrons. It's trying to get rid of electrons, right? So it's pushing electrons away from itself. It's donating them to some other atom, right? Why did when I broke the bond in the electrophile, why did I break it and give those electrons to oxygen?
You broke the bond in electrophile.
Mm-hmm.
Did you get
This one right here, this bond, I'm gonna highlight it. This arrow right here. Why did I give them the oxygen and not the other way? Think about it. What's the charge on oxygen?
For right now, it's
Is it not
well,
positive? The form of
it's
charge
positive.
is plus
So,
1. Go ahead.
so you're gonna make it neutral.
Exactly. Right? If it's positive, one of the other rules about writing mechanisms is I never push electrons away from a positive charge. I always push them towards a positive charge. Plus, in the CO bond, where's the dipole going? Is it going this way?
Toward the left.
Towards oxygen, right?
Yeah.
So anytime I have a dipole, the electrons in that bond are going to favor the atom that's more electronegative. So when I break that bond between those two atoms, the electrons are going with the more electronegative atom. Does that make sense? Let me show you. Let me give you a what are you doing? Sorry. All right, let me give you an example. So let's say I had a bond between, I'm just gonna throw another page in here, because this is stuff that you're gonna use in perpetuity, right? You're gonna use this for everything that we do from this point forward. Right, so let's say I had a bond between carbon and hydrogen, and I wanted to break it. Which way is the dipole for a CH bond?
Towards carbon.
Towards carbon. So if I break that bond, these electrons heterolytically now, not just breaking it, but still heterolytic. It's heterolytic cleavage, right? If I break that bond, the electrons are going to carbon. Are y'all following that? If I have a bond between carbon and oxygen, right? If I break that bond, the dipole is going towards oxygen. So if I break it, those electrons are going with oxygen, right? So I have, and this is all, let me put something right here. Right? If I break that, anytime I break a bond between two atoms heterolytically, the electrons are going with the more electronegative atom. Right? That's a rule of thumb. Right? If I have a bond like so with OH, I'm going to put an R out here. Right? That bond is going to be broken and oxygen is going to receive that pair of electrons. Right? Anytime I break a bond heterolytically, I'm going to break it and give the electrons to the more electronegative atom. Right? Are y'all following? We're good? So what type of bond breaking is this right here? When I broke that CO bond, is that homo or heterolytic? Are both electrons in that bond going to one atom?
Yes, it's
They are.
hetero.
So it's hetero. Anytime you use a double-headed arrow, it's going to be hetero, either lytic or heterogenic. Depends on what you're doing. If you're making bonds, it's genic. If you're breaking bonds, it's lytic. So anytime you see a double-headed arrow, then it's hetero. If you see a single-headed arrow, then it's homo. Right? So this would be homo, lytic or genic. Right? Any questions about that? The time, 11:34. I said I was going, in my mind, I said I was going to let y'all go early, but not this early. I feel like I'm doing you a disservice for your tuition fee and your fees. All right, let's go up here and let's look at some of these examples. Let's finish, when we finish these three examples, we're going to stop. All right, one of them we worked on in recitation last night. So I hate to erase this because I'm going to have to rewrite all of it, but I'll erase it. I ain't going to be lazy. Right? So this type of reaction, what is it? Look at the product, look at the star materials. I'm starting out with one of my reactants is a pi bond. Right, so anytime I'm starting with a pi bond and I'm adding a nucleophile to it, what type of reaction is that? Don't all speak out at once now, because we don't want it to be too noisy in the Zoom box.
Is it addition?
Yeah. Why you say that like you scared to say it? It's better to be wrong now than be wrong on the test. So if you say it and it's wrong, you get it corrected. If you don't say it and you keep the wrong thought when you take it to the test, then you can't get it corrected. So yeah, it's addition. And addition always involves a pi system, right? A pi bond. So where is my nucleophile in this reaction? Which one of those two is the nucleophile? And how do you know?
The one with the CH2, because it's more It has a negative charge.
Yes, it has a negative charge, and that carbon is a great nucleophile, by the way. I have a chart that I could show you how you can determine what's a better nucleophile and a better or better base, but we're not going to do that right now. I don't want to hit you with too much before the exam, but we'll do it maybe when we finish radicals. Or no, I'll take that back. We'll do it when we start substitution and elimination. All right, so this is my nucleophile. That makes this by default the electrophile. Where is that electrophile going to react? Where's the reactive site? What do you think? Where's the biggest dipole in that molecule?
Is it going to attack the carbon?
Which carbon? You're right. Definitely it's going to attack a carbon, but which one? Is it
The
going
one
to
under the oxygen?
that one? Yes, the carbonyl carbon. And the reason is because there's a big, giant, stinking dipole right here, right? Boom. So that carbon has a partially positive charge. And actually, if you do the resonance for it, it can be fully positive. So that's where your reactive site is. So when I write this here, like that, boom, right? That's going to give me this. Anybody not see that or disagree? So I made a carbon-carbon bond. That's the one that's highlighted in pink. And then I broke a carbon-oxygen pi bond, which is, I showed that by highlighting the oxygen in green with an extra pair of electrons because it had two lone pairs on the left side, here and here. And then the product, now you got three lone pairs. All right. So this is an example of a concerted mechanism, right? Everything is happening all at once. All right. So I broke a CO pi bond. I made a CC sigma bond. So this is the calculation down here. CO pi bond is 741. C sigma bond is 347. So that step is positive 334. So that means that it's going to be endothermic. It's going to have high activation energy, a positive Gibbs free energy, and the equilibrium constant KEQ is going to be less than 1. All of that we know from calculating the enthalpy, delta H. Yes, no. All the bond forming and bond breaking in this example, what is it? Is it hetero or homo?
Hetero.
It's all hetero. All my arrows are double headed, right? So this is a polar mechanism, and everything is heterogenic or heterolytic. All right, let's do the last two. This actually is a combo, right? These two are part of the same mechanism. And I got something else I can sneak into you here too, but I'll wait. All right, what do you think? What's the first step? And let's put the arrows in. What happened in that first step? You have the product over here. What happened going from the left to the right?
The bond is broken between carbon and oxygen.
You in this top example right here?
The lone pair from oxygen is transferred to hydrogen.
Okay, what do we call that? In
Proton
scientific,
transfer.
proton transfer. Good. So we got a proton transfer step here. which is indicative of acid-base chemistry, right? Not nucleophile, electrophile chemistry, even though the proton could be considered an electrophile and the oxygen could be considered a nucleophile. All right. So for that step, what did I do? Did I break any bonds?
Nope.
No. So bonds broken would be 0. And then did I make any bonds? I made an OH bond, right?
Right.
So that's OH, which is, I want to say 464, but I'm going to double check. Yeah, it's 464. So the OH bond is 464. Right? So what is the delta H overall for that step?
Negative.
Negative 464. Good. Because bonds broken is 0. 0 minus 464. So it's negative 464 kilojoules per mole. All right. What do we know about that? What can we say about it overall? Exo or endothermic?
Exo.
Exothermic, highly exothermic. So low activation energy, right? Low KEQ greater than 1. The Gibbs free energy is negative, just like the enthalpy. And it's going to be a fast reaction. So now in the next step, what's happening going from here to here?
That bond between carbon and oxygen is being broken.
There you go. Now you got it. You're on time with it that time. You was earlier.
Yeah, I don't know what I was looking at.
That's okay. All right, so that's happening. So let me zoom in. Sorry about that. I'm breaking the CO sigma bond. Is that right?
Right.
How? Homolytically or heterolytically? Ooh, that's a mouthful there.
Hetero.
Heterolytic cleavage of the CO bond. So my bonds broken would be a CO single bond, and then my bonds formed would be 0 because I didn't make any bonds on the other side. Following?
Mm-hmm.
So the CO single bond, I know we just got that somewhere.
It's 360.
360, good, thank you.
You're welcome.
So this is so bonds broken is 360 minus 0. So the second step is plus 360. Is that right?
Mm-hmm.
What's the overall? If I took those two numbers.
Negative.
Go ahead.
It's negative 104, so it'll be exothermic.
Okay. Negative 104 for delta H for the reaction. Good. So the overall process is exothermic. What if I ask you to build a energy diagram? What would it look like? If the first step we did up top was negative 464, that's exothermic, is that right? And the second step is endothermic, yeah?
Right.
So let's see if we can do it. We can just build it right here. So the first step is going to be really fast. And a big energy difference between the reactants and the products too, if it's negative 464. Right? And then the second step is going to be a little slower, right? But the overall is going to be exothermic. So that means that the products are still going to be lower in energy than the reactants. And then this is intermediate in between those two steps. And then at the top of each one of these humps is a transition state where your bonds are being made and being broken. then time and energy, time on the X, energy on the Y. And that's that. All right. Any questions about that? That overall, that is a stepwise process as well. Right. Any questions about that? What do we call this species right here that we made? Anybody? What do you call a carbon with a positive charge on it?
Carbocation.
Yes, carbocation. That's a very important species to remember. And this is a tertiary carbocation, right? I'm just putting it there because it's something you're gonna see again. Not on the exam, but just later on, you know, as we matriculate. It's tertiary. Why is it tertiary? Did somebody tell me that? Now that's something we already learned from a month ago.
It's
Is it
because the
because it's
number of
attached to 3
carbons.
carbons?
Yes, I think both of y'all was saying the same thing. You got 3 carbons attached to that carbon where the plus charge is. All right. As a mental note, the tertiary carbocation is one of the most stable carbocations that you can make. It's very stable because all of those carbon-carbon single bonds are pumping electron density towards that plus charge, trying to stabilize it. Right? So it's very stable. The more carbons you have around that carbocation, the more stable it is. When you start taking carbons away, then it becomes less stable. All right? That's just a little nugget for you because you're going to see that again a lot when we get to alkenes. What do you think the least stable carbocation would be? And we're going to end on that note.
The primary one?
Yeah, well, yeah. Okay, I agree with you there. But there's one that's even less stable than that, and it's called a methyl carbocation. So like just a CH3 with no carbons attached. And then we'll go primary, secondary, and then tertiary. This is the least. And then this is the most. Right? Methyl is the least, followed by primary, secondary, and then tertiary. So good, that's a good answer. I appreciate that. You're absolutely right. All right. So we're going to stop here. I said I was going to let y'all go early. So I'm going to give you 10 minutes to do what you do for your next class. You should get an announcement when the exam opens. It should open at 12:30, I think, something like that. But you'll get an announcement. Make sure when you turn your file submissions in, make sure that they are PDF only. Make sure your name is on it. And this test is a little different. It's broken up A through N and then M through Z. Or A through M, I'm sorry, and then N through Z. So make sure you take the right version too, based on your last name, not your first name. All right. Any questions about anything? Oh, I see it's red microphones. I guess that's Friday.